crew, this is our last set of notes for Unit 4. Well, it's part 1 for Unit 4.4. I'm going to start these today. We'll finish them with a small piece tomorrow. I want you to know how proud I am of you. This is a big chapter. It's got a lot of big ideas in it, and we're not just learning those big ideas, we're using those big ideas to solve problems. You are a great group of kids. You're so smart. You're working really hard, and you are getting stronger every day, right? Those brains are getting bigger and more powerful every day. God made you to think well, and this is going to help you grow in your ability to think. So there are a lot of notes here. I'm going to go through a good part of them pretty quickly because they're a backdrop for what we're doing. So we're going to look at doing 3 things in these notes. And so for all we're going to cover, these are the 3 things that I'm going to want you to really grasp onto and be able to know and use. One is the criteria that we use for selecting what we call the principal branch, which defines an inverse trig function. The second thing is that we want to get then what the resulting ranges of those inverse trig functions are. And then finally, we're going to use those ranges to evaluate the composition of a trig function and an inverse trig function geometrically. So let's get started. What we already know what the graphs of the 6 trigonometric functions look like, right? So what we have here is we have the graph of y equals the sine of x. We have the graph of y equals the cosine of x. Both of those are waves with domains that are infinite, right, from negative infinity to infinity, and from ranges from -1 to 1. So one thing we'll notice, and I want to look at cosine because we're going to look at its inverse first, is we know that the cosine has a y-intercept at 1. We know that it completes one cycle between 0 and 2 pi. And in the space from 0 to 2 pi, it hits every y value between -1 and 1. Right? The other trig functions that we're also familiar with, we know what the graph of the cosecant looks like and the secant, both inverses of sine and cosine respectively. And we know what the graph of y equals the tangent looks like and y equals the cotangent, both S-shaped waves, right, with periods of pi units equivalent to 180 degrees. So for example, in our cotangent, that repeats itself between 0 and pi, right? In the next, between pi and 2 pi, we get a repetition of that graph. So we're familiar with those graphs. Now, the other thing we know is that the graph of the inverse of a function will switch its x and y's. So if we're going to look at the graph of y equals, this is the arc cosine of x, then we're going to get a graph that instead of having domain from -infinity to infinity, its range is going to be from -infinity to infinity. So this goes, right, forever below and above. Its domain will be the range of the cosine, which is between -1 and 1. So it goes to the left to -1 and to the right of 1. You'll note that instead of having a y-intercept at 1, its x-intercept is at 1. And then we follow this sideways wave until it starts repeating itself. And it's going to repeat itself after 2 pi units along the y-axis, right? So this wave goes between 0 and 2 pi. Now as we look at this graph, you're going to note that the graph of the arc cosine is not a function. Why is it not a function, right? It doesn't pass the vertical line test, right? So no, it doesn't. This is a relation, a set of points, but not a function. Now, so keep that in mind. We're going to build on that. What's new to know is this. We know that the graph of the inverse functions, right, will be functions. They will pass a vertical line test. And those functions will be pieces of our graphs of our arc relations. And those pieces are called the principal branch of that inverse trigonometric, this should be relation. Okay, so what we're going to call this principal branch is going to be a piece of the graph of the arc relation. Now, there are 5 criteria for selecting those principal branch, and this is one of the things I want you to know is what those criteria are. The first criteria is that that principal branch must be a function, so it must pass the vertical line test. The second thing is it must use the entire domain of the inverse trig relation. So what would have been the range for the trig function, right, becomes the domain of the relation. It should be continuous if possible, and it should be centrally located, and by that we mean as close to 0 as we can get. And if there are 2 choices that are equal in each of these 4 previous criteria, except that one is positive and one is negative. So if we have a choice, then we're going to choose the positive branch, the one that is above the x-axis rather than the one that's below. So let's look at the graphs of the inverse trigonometric relations and functions. What we're looking at here, right, so this is the graph of y equals the arc sine of x. And I know it's arc sine because it has a y-intercept of 0. And we see kind of that hill turned sideways and then the valley. So this is our umbrella, this is our bowl-shaped curve. I'm going to erase that. So that's our arc sine, and I want to pick out the principal branch of this. So I want to pick out a piece of this function that will stretch from -1 to 1 that will pass the vertical line test. Right? I want a piece of this that is as close to the origin as possible, that's continuous if possible, and if I have a choice between positive and negative, I want one positive. Well, can you see a piece of that graph that stretches between -1 and +1 that would pass the vertical line test, that is as close to the origin as possible? Well, let's think. What if we started that piece here and we travel to here? Wouldn't that work? I hope you can see that it will. So our principal branch goes from here to here. And that is the graph, right? So this is the graph of y equals the inverse sine of x, which is a function. So let's look here. This is y equals the arc cosine of x. So I want a piece of this graph that would pass the vertical line test, that stretches between -1 and +1, that is close to the origin as possible, that is continuous, and if I have a choice between positive and negative, I want the positive. So let's think about that. I could choose this piece that goes between -1 here and +1 here. That would pass the vertical line test. It's continuous, it includes the entire domain, and it's as close to the origin here as I can get and stay on the graph. But if I think about that, I could also choose this piece that goes between here and here. That also stretches between -1 and 1, would pass the vertical line test, is as close to the origin as possible, as continuous. So between which of those two do I choose? Well, I choose the positive one. So what I have in pink here, this is the graph of y equals the inverse cosine of x. Okay, so all the way from -1 and 1. All right, let's walk through that process with our other graphs. So this is the graph this is the graph of y equals the arc sine of x. You can imagine that you could see that hill and then the umbrella between 0 and 2 pi, right? And then clipped and flipped over. I'm going to take that out. And I want to select my principal branch here. Now, to include the entire domain, I've got to go from negative infinity up to negative 1, and then pick up at 1 and go through positive infinity. So I want pieces that stretch, right, across those x values. I want a piece that passes the vertical line test, that's as close to the origin as possible, and that's continuous if possible. Now my problem is, for me to go from negative infinity to negative 1, I'm going to need a piece from these sections that are left, right? So from here or from here. For me to get a piece from 1 to infinity, I'm going to need a piece of either this section or this section. So it's not going to be possible for me to be continuous. But for me to stay as close to the origin, this is what I'm going to do. So let me clear this off. So if I take from here to the left, then I've got from negative infinity to negative 1. And then if I pick up and I take from here to here, then I have from 1 to infinity. Right? Those pieces would each pass a vertical line test. They're as close to the origin as possible. They contain the entire domain. They are not continuous, but that was just if it could be. And to be as close to 0, I've got part of it that's negative and part that is positive. So this is the graph. Let's take that off. Right? So this is the graph, right, between here and here. That's the graph of y equals the inverse cosecant of x. I'm sorry, this should have been the arc cosecant. No, I had it right. This is the arc, no, that's right, the arc cosecant of x. Okay, here we have y equals the graph of the arc secant of x, right? And again, you can kind of see your cosine curve going in between that. And for this, our principal branch is going to include this piece and this piece. Our other option would be to choose these two negative pieces, but between the two we want the positive, and that meets all our criteria. And between these two branches, we have y equals the inverse secant of x. Our last two are our arc tangent and our arc cotangent. This one, we have an increasing tangent increases, so this is y equals the arc tangent of x. And what I've shaded is actually the principal branch. That's a function. It's continuous. It stretches from negative infinity to infinity. It's centrally located. So this is y equals the inverse tangent of x. And then this is our graph of our cotangent, which is a decreasing curve. And so this is y equals the arc cotangent of x. And this branch is y equals the inverse cotangent of x. So make sure you know the 5 criteria for a principal branch, and you should be able to match. Well, if I give you one of these graphs of the arc-trig relation, you should be able to trace over the principal branch like I just did for you in your notes. Okay, now, for that, what we want to pick up on here is what the resulting range is for each of these trig functions. Okay, let's go back and look at these functions. So I'm going to come back to my inverse sine function. So my inverse sine function stretched from this location to this location. Well, if this is at pi, then this must be at pi over 2, and this goes an equal distance below, so that must be at negative pi over 2. So for my inverse sine function, it has a range from negative pi over 2 to pi over 2. Right? In the UV coordinate system, right, where this is U, this is V, that would take an angle, right, that goes from negative pi over 2, which takes us through the 4th quadrant, to positive pi over 2, which takes us through the 1st quadrant. So since the inverse tangent, right, the result of that is an angle, we can see that the inverse tangent will also always give us an output of an angle that is a 1st or a 4th quadrant angle, arranged between negative pi over 2 and pi over 2. When we look at the cosine, right, the results we get from it, the outputs, range between 0 and pi. So that inverse function has a range from 0 to pi. And for that, if we look at our UV coordinate system, right, where we put an angle, then we're going to get an angle that goes from 0 through to pi, which is going to be a 1st or a 2nd quadrant angle. When we look at our other inverse trig function graphs, we can notice that this cosecant is going between negative pi over 2 and pi over 2, that's its range. That the arcsecant is going between 0 and pi, so its range is between 0 and pi. That the arctangent, right, or the inverse tangent, has a range from negative pi over 2 to pi over 2. And the inverse cotangent has a range between 0 and pi. Okay, so what that gets us to is this. You need to know that the range for the inverse sine and for the functions that depend on that, so that would be the inverse cosecant, remember cosecant is 1 over sine, and for the inverse tangent, which is sine over cosine, right, that those ranges are all from negative root 2 over 2 to positive root 2 over 2. Which give us an angle that is in either quadrant 1 or quadrant 4. And this is the big thing that we're going to use with what we do next. In contrast, if we have an inverse trig function that depends on the inverse cosine, so inverse cosine, inverse secant, remember secant is 1 over cosine, or inverse cotangent, where cotangent is cosine over sine, that those ranges will be between 0 and pi, which means that they will have angles that are in quadrants 1 or quadrants 2. So, inverse sine, inverse cosecant, inverse tangent will produce a quadrant 1 or quadrant 4 angle, inverse cosine, inverse secant, inverse cotangent, an angle in quadrant 1 and quadrant 2. You want to know that, that's what we're going to use. So, moving on, this is how we're going to use this. Okay, so this is what we're getting to. We want to evaluate the tangent of the inverse sine of negative 2/3 geometrically. Okay, so we're going to do this from a graph. In order to find the exact value, right, and the exact value means we're going to do that without calculator. And then we'll check our answer numerically, that means, right, with our calculator. So this is how this is going to work. So I'm going to come in here and I'm going to start on the inside. So I'm going to start with this inverse sine of negative 2/3. We know that the output for this is an angle such that the sine of that angle will equal negative 2/3. Now, the other thing we know is that the inverse sine gives us an output, right? The output of this angle is going to be a quadrant 1 or a quadrant 4 angle, which means that my answer is not going to be in quadrant 2 or quadrant 3. So if I have a quadrant 1 angle, I know that my sign will be positive. My sign will be negative in quadrant 4 because sign depends on y, and y's are negative in quadrant 4. So I know that the angle that I'm looking for will be a quadrant 4 angle because the sign is negative there. And that there will be a point on the terminal side that will have coordinates uv, and there will be a radius here. Now we know that the sign can be found by taking v over r. Right? Because of that, we know that v could be -2, so our second coordinate -2, and r then would be 3. R would be 3. Using that, we know that u squared plus v squared will equal r squared. So plugging in 3 for r and -2 for v, that says -2, we can find u. So I get u squared equals u squared plus 4 equals 9. So u squared must equal 5, which means u must equal plus or minus the square root of 5. Since u is on the right side, I know that it's going to be the positive square root of 5, right? If it were on the left side, it would be negative. Now, I want to find, from here, I want to find the tangent of my angle. And I know that I can find the tangent of an angle by taking v over u. We have our v is -2. We have our u is the square root of 5. So therefore, we know that the tangent of the inverse sine of -2/3 will equal -2 over the square root of 5, and that's our answer. Okay. So there are many steps to this. We're not doing anything hard, but we do have to remember those things that we've learned. Okay, let's look at another example. Actually, I think for today we can stop there, and we will pick up with this other example tomorrow. Okay, so that's where we are. Do the things you need to do from here, and I will see you tomorrow.